Hi everyone, this is a video looking at some more angles inside circles. We're going to be focusing on isosceles triangles with inside circles. So we've got a couple of questions here to complete. First of all, as a starter, if you do those first and then come back on for the answers, please. Right, part A here is dealing with the circle or triangles inside circles stuff that we were looking at on Thursday, and we did some on Friday as well. So the main thing to notice here is that we have a diameter going through the centre of the circle and two lines coming from the diameter which make up the triangle. Therefore, up at the top of this triangle we have a right angle. So if we have a triangle, one angle is right angle, the other angle is 30, we can do 180, subtract 90, subtract 30 to find our missing angle. If we do that process, we should get 60 degrees as the missing angle in here. Part B is looking at isosceles triangles. We will need these rules to complete the questions today. So therefore, we have two sides of this triangle that are the same. Therefore, two angles in the triangle are the same. The angle where the two sides meet is the one that is different. Therefore, the 40 is the same as the 40 down the bottom there. So the two angles down the bottom of this triangle are the same size. And the angle up the top of the triangle then is 180, take 40, take 40. Therefore, up here we have the angle of 100 degrees. Next, we have a question here. So, again, we have an isosceles triangle. The two sides that are the same meet at the angle which is different within the triangle. So therefore, the two angles down the bottom of this triangle, again, are the ones that will be the same size. So we can find those two angles by saying 180 take 50. That's the only angle we have in the triangle. That gives us 130. Both of those two angles have to add up to 130, but they also have to be the same size. Therefore, we can find those by halving 130. And that will give us 65. So 65 degrees in that one and 65 degrees in that one. You have to know those methods off by heart. So B and C. If you're not sure of those, then you're going to have to go all the way back to when we looked at angles in angles and triangles a good few lessons back now. So on to today's notes then. As I said, we are looking at isosceles triangles inside circles. Now, we are going to be using some circle facts as well. In this diagram here, we are shown that our blue lines on the right hand side of that diagram there, our two blue lines are both radii. So both of them come from the centre of the circle and they go right over to the outside, the circumference of the circle. Therefore, both r's are a radius each and therefore are the same size. Any line that comes from the centre of the circle to the outside, any of those that I'm drawn in with the black, they're all radii, which means they all have to be the same size. Now, the line in red on this diagram, AB, is what's known as a chord. So a chord is a line that joins 2 points on the circumference. A diameter is a special chord because it joins the two sides of the circle. It still joins 2 points in the circumference, but it goes right the way through the middle of the circle. So it's still a chord, but it just has a special name because it has other conditions on it as well. So another chord of this circle might be up there, or another one might be along there. As long as the straight line joins two sides, 2 points on the circumference of the circle. Now, that definition is not necessarily something that we have to know just now, but it's part of the circle, so that's why it's mentioned in this slide. So let's have a look at how these isosceles triangles can be calculated within circles. In this diagram here, we are given a circle We know that the point in the middle is the centre of the circle. Therefore, the two lines coming from that point are going to be both radii. Now, it doesn't matter what length those sides actually are, it just matters that they are the same size. So if those are the same size, then the red outline there forms an isosceles triangle. All we need to find now is the two angles which make up the other angles in the triangle. We know that those have to be the same size, so if we refer back to our isosceles triangle calculations, I can do 180 take away 100, as that's the angle that I'm given in the triangle already. That gives me 80. The two angles here have to add up to 80, they have to be the same size, so they both have to be half of 80. Therefore 40 in here and 40 at the other one as well. Now you can always check this calculation at the end of your question. So you can say 40 plus 40 plus 100 if they all add up to 180, and if your two angles at the ends of the same sides, the sides are the same size, are also the same, then you've got an isosceles triangle and you should have got the calculations correct. Okay, so you can always justify that to yourself at the end. Add them all up, but also make sure that your two angles that should be the same size are in fact the same size as well. Another example of this then is this question here. So we're looking at two radii coming from the centre of the circle. They are joined into a triangle with the chord AB, but what we're really using is the isosceles nature of this triangle. So if we have 32 degrees down at the bottom of the triangle, that means also at angle A we have to have an angle of 32 degrees. That is known by the two similar lines. So you can see the two lines through here mean that those lines are the same size. If those lines were not there, it wouldn't matter because we know that they are both radii and therefore have to be the same size. Now, if we do 180, take away 32, take away 32, then we'll get 116 degrees for the angle in the side. So what I'm really asking you to do for each of these diagrams and the examples is to work out all of the missing angles inside the triangle. The last one here, so this is how it may be presented to you within the worksheet. You are not told that these two lines are the same size, OA and OB. However, we can see that from the nature of the circle, they are both radii, so must be the same size. Therefore, it's the same calculations as we had in the first example. We know one angle in the triangle, so we can take that away from 180. So 180 take 88 will give us 92. 92 has to be the remaining angle, so both angles at A and B have to add up to 92. We know from the isosceles nature of the triangle they have to be the same, so they both have to be, in this case, 46 degrees. Again, go ahead and add those up so you know that 46 and 46 are the same size, like they have to be for the triangle to be isosceles. Add up 46, 46 and 88 and make sure that they do add up to a total of 180. Justify that to yourself once you do the calculations later on from the worksheet as well. Now, the questions you see in the worksheet are going to be, in some cases, a bit more complicated than this. You're always looking for radius, so a radius in the circle that relates to a triangle. If you can do that, you'll be able to find isosceles triangles, and therefore you can find out the size of one missing angle easier than you would be if you had to try and find them all separately. Okay, so I want you to go ahead and try that worksheet just now. Please let me know if you've got any problems. Come back onto the live call if you have to, and we'll answer any that you need to. Okay.